Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through axiomatization. What actually is that? Well, axioms are rules that people use in mathematics. They're like the starting point, things that are assumed to be true. Now, for many centuries, there were many topics in mathematics where mathematicians operated without these rules. So what generally happens is people come along and formalize it. They come up with some rules that we know to be true. So we're going to look at axiomatization in set theory. So two of the people who did this were Peano and Dedekind. I actually don't know whether or not they were the first, but they came up with a list of rules for set theory. And we're going to look at the rules they applied to arithmetic sets. Sets in which you can perform arithmetic on their elements. One such set is the set of natural numbers. So before we go any further, we need to define the successor function. So the successor of a number k is just k plus 1. The successor is just the next, in this case, natural number. So the successor of 4 is 5, the successor of 20 is 21, and so on. Again, we're looking at the natural numbers. So the Dedekind-Peano axioms, there are actually quite a few. They're listed in the notes. We're just going to look at these two here. So these axioms apply in our context to the natural numbers. They are rules that we hold to be true. See, we've looked previously at axioms of the real numbers, like that addition is commutative. So in the real numbers, you can't really prove that addition is commutative. It is just something that is assumed to be true, something that we just know is true. It's one of the starting points. But it turns out if you start with a different set of axioms like these ones, you can actually prove things about the real numbers. You can prove axioms of the real numbers if you start with a different set of axioms. So we're going to look at an example where we use mathematical induction to prove that 0 plus n equals n for all natural numbers n. So this existence of an additive identity, when we're talking real numbers, it is an axiom. Can't be proved or disproved. But now, when we start with a different set of axioms, we can actually prove this. See, one of the Dedekind-Peano axioms is that x plus 0 equals x. But that's different to 0 plus n equals n. So this alone doesn't prove that 0 commutes with every element. So we're actually going to prove that it doesn't matter whether 0 is first or second in the addition, it's still the additive identity. And we're going to need these two axioms to prove this. Of course, most of us would look at this and say, yeah, of course that's true. Why do we need to prove it? Well, apart from the formal rigor that's important in mathematics, this is actually really important in AI, artificial intelligence. So even though humans don't need this level of formality to know something is true, turns out that in AI it does. So what is this mathematical induction? Well, mathematical induction is like having a set of dominoes. So what we do is we prove that the first domino falls, then we prove that if any domino falls, the next one falls. What our basic strategy here is, we're going to prove this is true when n equals 0. We're going to prove that if it's true for n equals some number k, then it is true for the successor of k. We're going to prove if it's true for n equals k, it's true for n equals k plus 1. And that is enough to prove that it will work for all natural numbers. Because if we prove what I just said, we've proved that it works for n equals 0, then it will work for n equals 1, n equals 2. If it works for n equals 2, it'll work for n equals 3. If it works for n equals 3, it'll work for n equals 4, and so on. So this is how we start it. The first thing we're going to do is we're going to prove it's true for n equals 0. So if n equals 0, we just have 0 plus 0. So by this first axiom here, x plus 0 equals x. So this is like our x. X plus 0 just equals x. So we have proved it is true for n equals 0. The next step is we assume that it's true for n equals k, where k is some natural number n. So what we're doing is we're assuming that 0 plus k equals k for some natural number k. K could be 3, 5, 9, whatever, it doesn't matter. Now what we have to show is that if it's true for n equals k, then it must be true for n equals k plus 1. So let's look at what happens when we add 0 and k plus 1. Well, we know that k plus 1 is just the successor of k. It's just the number that comes after k. So we can rewrite this as 0 plus the successor of k. Now we're going to use this second axiom here. So it says that if you have x plus successor of some number, it's just the successor of the sum of those numbers. So here we have like 0 is our x and k is our y. So by that second axiom, if that second axiom is true, and we assume that it is true, we end up with the successor of 0 plus k. But because of our inductive hypothesis here, because we assume that 0 plus k equals k, then this must just be the successor of k, and the successor of k we know is equal to k plus 1. So we have proved that 0 plus k plus 1 equals k plus 1. Here's a rundown again of what we proved. We proved that this statement is true when n equals 0. We also proved that if this statement is true for n equals some number k, it's true for the successor of k. If it's true for one number, it's true for the next number. So because it's true for n equals 0, it must be true for n equals 1. Because it's true for n equals 1, it must be true for n equals 2. And so on. It's true for n equals 3, n equals 4, and so on for all natural numbers n. This is the process of mathematical induction. We've proved something that is an axiom of real numbers when we've started with a different set of axioms in set theory. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.